This video is going to show you some special examples that we might want to use in graph theory. Basically, if we're trying to analyze a problem, trying to find a formula that might work, or trying to find theorems if they apply or not, we're going to want to look at these examples and see what works and what doesn't work, and that can give us a lot of intuition about the problem. The first of these is called the complete graphs. And the idea for a complete graph, and we'll start with K2 here, is K2 will have two vertices, and every possible pair of vertices are connected. So it's not particularly interesting for K2. K3 will have three vertices, and again, every possible pair will be connected. And if we go to K4, that will once again have four vertices, and every possible pair of points are connected. And it starts getting really interesting when you have things like K5 here. Now you're going to have five vertices, and again, every possible pair is connected. Now, if you're trying to draw this yourself, so you're not sure, how do I draw it most efficiently? Once you get your points there, start at 1, say the top, and say, I want to connect the top to every other one. And you say, okay, I want to connect this upper right one to every other node. And then this bottom right one connected to every other node. And then eventually you get down to just one line left, and there is your K5 graph. Now for cycles, we're going to start with actually C3 here, because you can't really form a cycle with only two vertices. So a cycle, you want to get right back to where you started from. K4, you have your four vertices, and you just start at one point and go all the way around to get back to where you started from. That shouldn't be K, that should be C, apologize. And if you want C5, again, you just draw your five vertices, and you travel around, and you get back to where you started from. Now, for the wheels, they are very similar to these cycles. And you might be bothered here by the fact that my W3 is actually going to have four vertices. And that's because you're going to start with the cycle C3, and then you're going to add a middle point that connects to everything. So if I want my W4 here, you start with your cycle 4, and then you add a middle point, and the middle point just connects to everything. If you want your wheel 5, you start with your your cycle 5, and then have a middle point that connects to everything. Okay. Now, for cubes, these are a little bit trickier to draw when you get to higher numbers. So Q2 is, I'll just start with Q1. Q1 is what's called a one-dimensional cube, which you might not call it a cube because it doesn't look like one, but it's just a line here. Q2 is the two-dimensional version. So in this case, it's a square, same as C4. And then if I want Q3, this would be a three-dimensional cube. This is what you normally think of when you hear the word cube. And we'll see if I can draw it well here. And so the idea is, it's 3 dimensions. It's got this kind of depth to it. And I know it's pretty poorly. And then we do have things like Q4 and Q5, but they are a lot trickier to draw because it's hard to draw things 4-dimension, 5-dimension, and so on. So I'll stop it there. But it's just something to keep in mind that we have these. The last version is called the complete bipartite graph, and I think the best way to explain that again is by an example here. So there's two numbers for a complete bipartite graph, m and n, And what this corresponds to is, remember bipartite, we want to split the vertices into two groups, and we want to have connections between the groups but not within one group. So K23 means that you have a group of 2 vertices and a group of 3 vertices, and the whole complete means that you have every possible connection between them while still making sure you are bipartite. So this right here would be bipartite. The left side would be one group, the right side would be the other group. Similarly, if I wanted K, 3 to 5, I would have 3 vertices on one side, 5 vertices on the other. And again, we want every possible connection between the two sides, but no connection that's wholly on one side, because if you did, it would not be bipartite. So something like this. So these are all the standard examples. I will be referencing them quite often in these videos. I really recommend you learn these examples and understand them completely. Also, I'm not going to list them right here, but you can kind of work out formulas for things like how many vertices are going to be in a given Kn or Cn or Wn. You can work out a formula for how many edges are going to be in a given Kn or Cn or Wn. You can work out a formula for degrees of vertices. There's lots of formulas you could figure out for these graphs. I'll give you one of them. For example, if you have a complete graph, if you want to find the number of edges, it's going to turn out to be the combination number Cn2, because we're trying to have every possible edge that connects 2 vertices. So that means we want to count how many ways can we find 2 vertices. That's Cn2, and every one of them is going to be exactly 1 edge. Like I said, you could do the same thing for all of them. I'll let you guys work on that and try and see if you can figure out the formulas. But regardless, you definitely want to know these examples.